Sample problem 10, springs in series. Two steel springs are arranged in series as shown. The upper spring has 12 turns of 30 mm diameter wire on a mean radius of 130 mm. The lower spring consists of 10 turns of 20 mm diameter wire on a mean radius of 90 mm. If the ultimate shearing stress in either spring must not exceed 450 MPa, compute the maximum value of P and the total elongation using factor of safety equal to 2.0 and determine the equivalent spring constant to be using G to be 83 GPa. Given in the problem is two springs and the dimension of the first spring, it has 12 active coils. The wire diameter is equal to 30 mm and the mean radius of the coil is equal to 130 mm. For the second spring, we have 10 active coils. The wire diameter is equal to 20 mm and the mean radius of the coil is equal to 90 mm. Also given in the problem, the maximum shearing stress is equal to 450 MPa. The factor of safety we'll be using is 2.0 and the modulus of rigidity for both materials is 83 GPa. We're required to determine the maximum value of P, the total elongation, and the equivalent spring constant. So for us to determine the maximum value of P, we actually have two cases. The first case is for the first spring and the second one is for spring 2. The governing equation that will lead us to determine the value of P will be the determination of the shearing stress for the spring. So that's equal to the allowable shearing stress, that's equal to tau max over the factor of safety. And all of which should be equal to 16 PR over pi d cubed. Then we multiply the whole term by the wall factor. In most cases we'll be using wall factor in our designs unless it's indicated in the problem that we'll be using another uh, factor in our design. So for spring 1, we determine the spring index to be the diameter of the mean diameter of the coil divided by the diameter of the wire. So that's equal to 2 times the mean radius of the coil in spring 1 divided by the wire diameter in spring 1. So M, or the spring index, is equal to 8.667. Then we use the formula mentioned earlier. We have 450 MPa divided by the factor of safety, which is 2. That's equal to 16P times the mean radius of the coil divided by pi times the diameter of the wire. We raise that to the power of 3. And the whole term is multiplied with the wall factor. We determine the value of P to be 7,850.5 newtons if it's based on spring 1. For spring 2, we do the same thing, same process. We determine the spring index to be 9 and using the same formula and applying the correct dimensions for spring 2, we have P determined to be 3,379.268 newtons. We have determined two values of P and 4 design values to keep our assembly to be safe. We determine the value of P to be 3,379.268 newtons. We select the value of P which is the lowest. For the second requirement, you're required to determine the total elongation. So the total elongation is simply equal to the sum of the individual elongations of the spring. So I think that's quite visible enough that the total elongation should be equal to the individual elongations of the spring. And the same force is experienced by each spring because they're connected in series. Therefore, our total elongation is simply equal to the elongation of the first spring and the elongation of the second spring. We use the formula G PR cubed times N over G d to the raised to the power of 4. And we'll be using the same value of P that we have derived earlier. Therefore, we have the total elongation equal to the first elongation of the first spring. So we have 64 times 3,379.268 newtons times 0.13 meters raised to the power of 3 times 12 active coils. And we divide that with the modulus of rigidity, 83 times 10 to the power of 9 Pascal, times the diameter of our wire, and we raise that to the power of 4. And then we do the same thing for the second term, but we apply the dimensions for the second spring. So the same force is applied. Still, this is 3,379.268. So they should be the same. And we use the mean radius as 0.09 meters and the wire diameter to be equal to 20 mm or 0.02 meters. We raise that to the power of 4. Therefore, we have the total elongation is equal to 0.203533 meters, or in terms of mm, we have 203.553 millimeters as the total elongation. Now for the equivalent spring constant, by definition, spring constant is just equal to the force applied and the corresponding elongation due to that force application. Therefore, we have P over delta, that's equal to 3,379.268 newtons divided by 0.203533 meters. And you'll be obtaining 16,603 Newton per meter, or we have 16.603 kilonewtons per meter as the spring constant.